Hi guys, welcome back. Let's go through another example of electrical systems. In this circuit, you see that I have R, L, and C elements in series. So they are R, L, C elements in series. And I want to model this system using my four-step approach that we had in the example 1. Okay, let's get into it. Step 1, I'm going to list the elements in the system. So, inertia, stiffness, friction, my sources, and the number of ODEs. Okay? Now, if you remember, inertia elements in electrical systems were the inductors. I have one inductor in this problem, and I'm going to list that inductor as my inertia element. Similarly, my stiffness elements were my capacitors. I have one capacitor here, and I'm going to list that capacitor as my stiffness element. Friction elements were the resistors. They are responsible to kill the energy in the system. So that's going to be my resistor. And the source for this system is external voltage, which I'm going to show it with En. And at last, I would get to define the number of ODEs. If you remember, the number of energy storing elements in electrical systems will define the number of ODEs. Therefore, since I have two energy storing elements as the inductor and the capacitor, I'm going to end up with two ODEs. Okay, let's go ahead and find those two ODEs. I'm going to go to step 2 at this point. In step 2, I'm going to define the dynamic variables. So, what were dynamic variables? We have two types of dynamic variables. Yes, voltages across the capacitors and currents through the inductors. Now, because I have a capacitor here, the voltage across that capacitor is going to be my first dynamic variable, and the current through the inductor is going to be my second dynamic variable. And you guys notice that since R, L, and C elements are hooked up in series, the same current that passes through the inductor passes through the resistor and the capacitor. With that in mind, let's go to step 3. In step 3, we are going to write down the ODEs for each energy storing elements. Yes? So, write down the ODEs for each energy storing element. Again, if you remember, I have two energy storing elements. Yes, my inductor and my capacitor. Let's go ahead and write down the equation first for the inductor. EL equals to L I dot L. And for capacitor, if you remember, the equation for capacitor was C E dot C equals to IC. Okay, at this point, I'm going to change my pen and I'm going to label these terms as good and not good. My good terms, again, to remember, my good terms were twofold. Either my dynamic variables or my sources. My not good terms were the ones that were not good terms. Basically, anything else. Okay, so I'm going to pick my red pen, okay, and I'm going to label these terms as good and not good. Okay, Let's go ahead. I dot L, is it good or not good? Well, again, is it dynamic variable? Well, I dot L is not my dynamic variable, but it's the time derivative of my dynamic variable, so it's a good term. How about EL? It's neither my dynamic variable nor my source, so it's not a good term. I have to rewrite EL. Okay. Now let's go to IC. Do you guys think that IC is a good term? Well, in this problem, if you look at IC, okay, it's not in your dynamic variable. However, if you see here, IC is the current that passes through the capacitor. That's going to be the same current that passes through the inductor. Yes? So, in fact, your IC is equal to IL. Okay? In a way, IC and IL are the same in this specific problem. Yes, it's not always true in this specific problem. Now, if this is IL, then IL is a good term since it's your dynamic variable. Now, let's check E dot C or EC dot. EC dot is the time derivative of your dynamic variable. If you look at here, one of your dynamic variables was the voltage across the capacitor. And that's exactly what you have here. Well, not exactly the time derivative of that, okay, which is acceptable. Now look at this. We have two parameters here, L and C. We don't care about them. They're constant numbers, yes? So let's call the first equation as equation Smiley. The second equation as equation Cyclope, okay? From Cyclope, you basically have one of the equations completed, okay? So bring IL to the other side. So from Cyclope, you have C E dot C minus IL equal to 0. Yes? There are two families here, C and IL. Each family has only one member. You can safely box this equation. This is one of the equations that you needed to find. The next one is basically the one that deals with the equation Smiley. So for that one, we need to rewrite EL in terms of our good terms. So let's go to step 4 and rewrite not good terms using KVL, KCL, and Ohm's law. Okay. Similar to the previous example, I would look at the system, yes? I would look at the system and I would see from the tools that I have, which are KVL, KCL, and Ohm's law, which ones I can use. Yes? Okay. If you look at this problem, you see that there are no junctions in this problem. So KCL is immediately out the window. You're left with KVL and Ohm's law. You clearly have one loop. Yes, you start from here and you clearly have one loop. So KVL is one of the options that you need to use. The other one is the Ohm's law. Since you have the resistor, then you need or you can use the Ohm's law if necessary. Yes? Okay. Let's go to KVL first. Okay. And just to remind ourselves, for KVL, we had two important conventions. If you move in the same direction of the current, the voltage across R, L, and C drops. If you move against the direction of the current, the voltage across RLC will rises. So that was the first convention. The second convention was if you hit the negative polarity of the battery first in your transverse, okay, then the voltage rises. If you hit the positive polarity of the battery first, then the voltage drops. Okay. Now, let's go ahead and walk on this circuit in the direction of the current that's shown to us, in this direction that's shown to us. And I'm going to work with the direction of current IL that was assumed and given to me. Yes? Okay. If I move in the direction shown, which is basically the direction of the current, do you guys agree that the voltage across the resistor drops because I'm moving in the same direction of the current? Also, the voltage across the inductor and the capacitor drops. And when you get to the battery, you see that you hit the negative polarity of that battery first, then the voltage rises. This is the second convention, yes? Okay, so let's go ahead and write down the KVL here. Okay, you will have negative ER, negative EL, negative EC, plus EN equal to 0. Very simple, yes? And similarly, from the Ohm's law, you will have ER equals to R, VI that passes through that resistor. If you look at the setup, you see that the same RI that passes through the inductor and the capacitor passes through the resistor. So this is going to be IL. Okay? Now, the whole idea was rewriting EL in terms of my good terms. Yes? So let's go ahead and isolate EL from this equation, from the KVL. So it's going to be EL equals to EN minus EC minus ER. Good? Okay. Now let's look at these terms. I have EN, which is a good term. It's my input. I have EC, which is a good term. Again, it's my dynamic variable. And I have ER here. ER is not necessarily a good term. Okay. However, you know that you can actually substitute for ER from the Ohm's law. Okay. And if you substitute for ER from the Ohm's law, let's call this equation as equation 1 and this equation as equation 2. If you substitute 2 in 1, you end up with EL equals to EN negative EC negative. Instead of ER here, I'm going to put RIL. Okay, let's look at this equation again. The purpose was rewriting EL as a function of good terms. Yes, EN already a good term. It's my source. EC is my dynamic variable. It's a good term. IL is a good term. And R is a constant. I don't care about R. Okay, so with that in mind, I have written EL in terms of my good terms. So let's call this equation 3. Okay, substituting 3 in a smiley will solve the problem. Substitute equation 3 in a smiley. You will have, let me rewrite smiley one more time. EL equals to LI dot L. Okay, now instead of the EL, I'm just going to put it from equation 3. Yes, so it's going to be EN minus EC minus RIL. Good? Okay. Now at this point, keep the input on one side, bring all the dynamic terms to the other side, okay, and flip their signs. So you will end up with LI dot L, or let's say EN equals to LI dot L plus RIL plus EC. Good. I just brought these two terms from the left-hand side to the right-hand side and flip their sign. Okay. Now I can box these equations, but before that, I need to do the sanity check. Yes? How many families do I have on the right-hand side of this equation? Well, you guys tell me. I have the family of IL, and I have the family of EC. Family of EC, it has only one member. However, family of IL, it has two members, IL and I dot L. And you guys notice that within the family of IL, the members do not have different signs. So we are good, and we can box this equation as our final answer. Note that EC was the only member of the family EC. Okay, and definitely there is no sign changes when you have only one family member. Good. Okay, that's about it. In the next video, I'm going to talk about something a little bit more challenging.